All right, this is the last section of chapter 12, 12.5. We are looking at arc length and curvature. We mentioned last time, or I mentioned last time, that we were going to talk about finding a way to describe how sharp a curve was at a specific point. And I mentioned it last time, and that we would come back to it again this time, and that's what's going to happen. A little aside from that before, we're going to do the arc length part. We have seen the formula for arc length in 2 dimensions before. Does anybody remember what it looked like? It's got a square root, you're right. I'm just going to write it down. This isn't even in my notes, so let's just hope I get it written down right. It's got a square root. And what it did was it took a derivative and squared it for the x component and the y component, parametric stuff, right? And then we did an integral. The length of the curve was between a and b dt. So that's kind of our reference point. I know it's been a little bit since we looked at that, but we did look at arc length for parametric equations. So we're doing this now for the length of an arc in space. So this is theorem 12.6. And it's the arc length of a space curve. Space curve, it sounds like Space Dad. You guys seen Megamind?
Space
Yeah.
Dad?
Space Dad, yeah.
What's Space Dad?
It's in Megamind now, you gotta go watch it. If C is
years ago.
yeah,
Oh man,
smooth curve given by R of t equals x of t I plus y of t j plus z of t k on the interval AB then the arc length is S equals the integral from A to B, just like the other one. And it has a square root, just like the other one. And it has derivatives that are squared. Just like the other one, right? But it has 3 of them. We have C prime. Now, that portion that's in between the integral symbol and the dt at the end should look familiar. What is it? It's magnitude. That's exactly right. So what this is it's the integral of the magnitude. And that should make sense. The derivative of magnitude, I should say. All right, magnitude of the derivative. I think my words in the right order. Magnitude of the derivative. So whichever formula you sort of like to think about, one of them is more explicit. We're going to find an arc length. Our R of t equation, or form, is 4 natural log of t squared 4t, and our interval is from 1 to 3. All right, so we're going to need some derivatives, so we'll start there. I'll switch screens after I do this. R prime, what would R prime of t be on this? 4 over t for x. Mm-hmm. 2t and 4. Awesome. Everybody good with that? Okay, and then we're going to find the magnitude of that. And let me copy this. Actually, let's do this. Have no fear, it's coming back. Here we go. We are going to find the integral of the square root of each of these components squared. Sum. I think I got all the words in there, but maybe not in quite the right order. All right, so we're going to find s. Actually, I'm going to move it down. So s equals the integral from 1 to 3 of the square root of, I'll write it out, 4 over t squared plus 2t quantity squared plus 4 squared dt. So we have 16 over t squared plus 4t squared plus 16 dt. I didn't do this in my notes, but as I'm observing it now, I think it might be easiest to notice that they actually have a 4 in common to all of my terms. So if you wanted to pull that 4 out in front and take the square root of it, that might be a nice thing to do, and it might also make it easier to identify what's going to happen next. So I'm just going to put a 2 in front here, which leaves me with 4 over t squared plus t squared plus 4 dt. So generally speaking, integration is not the easiest thing to do when you've got square roots involved. You went through a whole chapter back in Calc 2 of integration techniques. This one, however, is very friendly. Can you see why? There is a way you can factor it. Not only that, but the only way it would be useful is if it factored into a perfect square. And it is. So if we were to factor this and reduce it, not reduce it, but clean it up, we would end up having 2 over t plus 2 quantity squared. So that your square root and your squares, in fact, cancel, and you're able to actually solve it by hand. If there were, for example, not a 4 underneath there, like let's say, for instance, that this component at the end had not been 14, it had just been t. We would be at a place where the best we could do is an approximation with a calculator.
Where did the t squared go?
Hmm?
Where's the t squared if it's...
Hang on.
4t squared plus t squared, and it disappears.
Nope, you're right. Just a second.
We take the 2 out.
Plus t.
Wasn't it being?
Oh, it should have been t at the end, not 2. That's my problem. I just wrote that down wrong. I think it's written down wrong in my notes, too. Oh, no, it's not. It's just, it's because I took my 2 out, and so I'm confusing myself in my notes. There's a t at the end. There we go. Thank you for fixing that for me, Ethan. I appreciate it. Does that give me all my pieces? Easier to see if I do it like
No,
this.
2 over t times t equals 2. That was twice.
Yeah, but if you put it in that order, you can see where the components are coming from. Are we good? Yeah, perfect. Thanks, guys. Okay, cool. So we actually have 2 times 2 over t plus t dt. And we can integrate. You can distribute the 2 back through if you want. We didn't actually have to pull it out. We could have dealt with it where it was. It wasn't hurting anything. Just made the numbers a little bit bigger. So what's the antiderivative of 2 over t? 2 ln t. And then the antiderivative of t would be 1/2 t squared. And very nicely enough, we have a 2 we're going to distribute through in a minute. And we're evaluating from 3 to 1, or 1 to 3. So we have 4 natural log t plus t squared from 1 to 3. So I have 4 natural log 3 plus 9 minus 4 natural log 1 plus 1. And what do you notice? Yeah, the 4 natural log 1 is 0. And then our answer ends up being 4 natural log 3 plus 8. Okay, let me go back to what I was trying to say until we found out that I had an error on my screen. This is really friendly, right? That it happens to factor that way, so to speak. If the component had been different, if this 4, this is when I was wanting to, had been a 3, this wouldn't work. And the best we could do at that point would be an approximation from your calculator. And if you approximate this with your calculator, once you get it into this component form right here, obviously without multiple three-dimensional kind of things going on because we've got it in parametric form, you will get the same decimal approximation you would if you were to put this into your calculator and get a decimal approximation, and you could confirm it that way if you wanted to do so. All right, the other part of this section, so this is arc length. You're going to have, I think it's 4 problems on arc length. And then the other part of our section talked about finding curvature. So let me describe or define what curvature is computationally. So we're going to let C be a smooth curve. And it can actually be in the plane or in space. Given by the equation R of S. Excuse me. Then the curvature, I'm sorry, I should say R of T. I was trying to decide whether to show you both of the different formulas in your book, and I decided to just stick with the one that had T in it. Then the curvature K at T is. There are 2 formulas, and while they are equal, there are different processes to find them. So we have the magnitude of T prime divided by the magnitude of R prime, or, and these are equal, but the magnitude of the cross product of R prime with R double prime divided by R prime's magnitude cubed. Just as a rule of thumb, I guess, or whatever, this one tends to work nicely when you have a T value. It's not a hashtag, it's a number sign. When T equals a number. So there's going to be a couple problems where they're going to give you a T value, and this is a pretty nice way of using this formula is with the T value given to you. The other one tends to work better when you don't have T. So and can you guess, just by looking at the formulas, why the first one might be easier to work with than the second one? When T is arbitrary, that is, there's still a T in the problem. Can you tell the primary difference between the two? Maybe not primary, but a difference between the two.
There's no second derivative.
You got it, Andrew. Second derivatives. You guys had loads of fun on your last homework assignment where you had to find some second derivatives with T's involved, and they were messy, weren't they? And it's really easy to make a mistake when you're doing that many components of a derivative. So this first equation is actually friendlier when I don't have to find a second derivative because I still have T involved. Okay, so let's do a couple of examples. One of each of these types, I guess.
The cross product of R times its derivative, right?
R prime and R double prime. Yep, sorry. I hadn't realized that we were still writing, but I'll pause.
It's fine.
You're good? Okay. All right, so we're going to find the curvature. And the first one actually is going to have a point given. So r of t is t sine 2t, 3t, and it's going to be given that t is equal to 0. All right, so no matter which formula you want to use, you're going to find r prime, right? So let's do that first. What would r prime be for this vector? I'll start out 1. Now what? 2 cosine 2t and 3. And because I've got a t value given, we're going to use the second form over here. And we can actually find, eventually we're going to plug in t equals the 0 anyway. And so it'll be easiest if we go ahead and do that without arbitrarily using it all the way along, since we're only finding it for one t value. So what would this be at 0? I'll start you out. 1. What's the next one? 2 and 3. So vector 1, 2, 3. Nice. All right. This isn't too bad, actually, to find a second derivative of, right? No. In fact, the first piece is 0. What's the derivative of 2 cosine 2t? Negative 4 sine 2t and 0. Cool. And your second derivative at 0 then becomes what? Yeah, it's the 0 vector. So we'll write it out computationally here in a minute, but think with me. What do you suppose happens when you take the cross product of something with the 0 vector? It's 0. And what would the magnitude of 0 be? 0. Magnitude of the 0 vector would be 0. So k is 0 on this one. Yeah. Right. We don't actually have to do the bottom part of it. What's that? Right. There's no curvature. That's exactly what that means. If you think about two-dimensionally speaking, like when we're finding derivatives, right? When you find derivatives in 2 dimensions, a derivative actually gives you curvature, right? So what happens when you get a derivative that's 0? There's no curve. I mean, the curve has stopped, right? It's changing direction, those kinds of things. Same idea, okay? So let's finish the problem. Just for the sake of having done it, I'll go ahead and find for us r prime of 0's magnitude. So if you were to find the magnitude of this, what was 1, 2, 3? You'd have the square root of 1 squared plus 2 squared plus 3 squared. 9, so what do we have? Is it 14? Yeah, something like that. Let me see if I find it on here. 14. And like we said, the cross product of, sorry, you bet, r prime of 0 cross product with r double prime of 0, well, is the vector 0. So we have the magnitude of the 0 vector divided by the square root of 14, this is k, and we get 0. Yeah? It is. It doesn't matter, but yeah, it is. You're right. Good to go? Okay, so super, I don't say super friendly, but it's kind of nice when you have a t value given because you can plug it in. You don't have to deal with the arbitrary t for quite as long. The other problem, we are going to deal with an arbitrary t in it. So, same directions. We're finding curvature. And our r of t equation is 4 cosine of 2 pi t I plus 4 sine of 2 pi t, j. And I think I'll just write up here in the corner, k is the magnitude of t prime of t divided by the magnitude of r prime of t. All right, for starters, we need a derivative. So let's start there. What is r prime of t?
Negative
Mm-hmm.
8 pi sine of 2 pi t.
Mm-hmm. Good job. And then positive 8 pi cosine of 2 pi t j. All right, I wrote the formula up here, but I didn't write the formula for t. Do you guys remember what your formula for t is? You just did a homework assignment on it. So how do I find t? Say it again.
R prime of t divided by magnitude of r prime.
Cool. So I also need the magnitude of r prime, right? And it won't just be a number. It will have t still in it. So,
Quick question.
yep.
Sine squared 2 pi t plus cos squared 2 pi t, does that still equal 1?
It will. Yep, it will. All right, so let's take a look. We have and the reason it will, Ethan, is because you won't have the i's and the j's there, right? This turns them into numbers. We're turning it to a magnitude. All right, so we have negative 8 pi sine 2 pi t squared plus 8 pi cosine 2 pi t squared, all under a square root. Beautiful things happen, right? Lots of beautiful things. Number one, there's no negatives anymore. Squaring things is nice. I've got sine squared plus cosine squared, like Ethan noticed, and that equals 1, right? So cool stuff. So if you would like to sort of identify it a little bit more clearly, there's an 8 pi here that's squared, and then it's square rooted. So there's an 8 pi that gets to come out of that square root. Kind of like I brought my 4 out a little bit ago as a 2. And then I really here still have sine squared of 2 pi t plus cosine squared of 2 pi t. And that is equal to 1. So my magnitude of r prime of t is actually just 8 pi. So what is t of t then? Let me highlight the pieces that matter. It's this piece divided by 8 pi. Yeah, right.
Wait, there's still a pi on the outside?
You have a pi on your side.
Oh, sorry. Negative is what I meant to put there. Tell my students all the time when I'm presenting they can't do the erasing, and I just did it, so let me move it. Okay. T, J. Okay, does that look right? I got my pieces in there. Okay, so we're making progress. We have found T. And I don't know about you, but if you take a look real quick and ask yourself, do I really want to find R double prime of T? It gets messier as you go. It wouldn't be horrible, right? I mean, we could do that, but then you'd have to do the cross product with T's still involved, and that does start to become quite cumbersome and probably not something we want to deal with. I have T of T, and I also now need T prime of T, right? Okay, so I need the derivative of the vector I just found. So what's the derivative vector for this? Looks good? Did my J show up? Yeah, okay, good. All right, so I actually have that part done, right? Don't I? Oh, I haven't, yeah, I did. The magnitude, I just didn't label it right, did I? Here. There we go. Now it's labeled, right? Yeah, and we're going to do the exact same thing for t prime, right? So I'm going to find the magnitude of t prime of t. These are supposed to have vectors like that. And wouldn't you know it, it's going to look really similar, right? Because that's what, sines and cosines do. So we have 2 pi cosine of 2 pi t squared plus negative 2 pi sine 2 pi t squared. Sorry, that's it. There we go. I can pull a 2 pi out just like I did last time because there are no more negatives. And I have left, yeah, cosine squared and sine squared. This is 2 pi. Can you find the curvature? 2 pi over 8 pi, which looks mysteriously like 1/4. That'll be a curvature. All that for a 1/4. That's true. Are you ready for your last homework assignment in Calc 3?
Wait, we're done?
We're done.
Wait.
Wait. Page 860. There are 4 web assigned problems. They're out there. I got it done. 1, 4, 9, 12, 30, 33, 38, and 39. And your question last time about S versus T, I looked through the resources in the book, and there's no explanation. They just use S instead. There was something that was interesting as I was preparing this lesson, though. We are working with finding curvature at a given point for any arbitrary parameter T. They do define it another way as well, so if you happen to go look in your book and you see another formula, they're defining it for a parameter S, but that one they specifically define, and S is in terms of arc length, right? Do you see our S over here? And they talk about how to do curvature in terms of arc length as well. So that was not in the last resource that I did, so I decided that we would just do it in an arbitrary fashion instead of doing it specifically for the arc length because it will cover all bases anyway. So that's what I decided. All right, did everybody get the homework assignment written down? Sorry, I switched slides on you. All right.